Okay, hello everyone. Welcome back. Let's commence with the lecture today. I'd like to change the subject a little bit from what we were studying before. I would like to give a kind of primer or background presentation on the classical differential geometry and tensor analysis in Euclidean space. In other words, the space of our common experience, three-dimensional Euclidean space. The reason for this lengthy digression is that understanding the basic ideas and tools of differential geometry will afford us a very interesting interpretation of aspects of plastic deformation, such as dislocation, density, and the consequent incompatibility of the elastic strain, and so on, later on in the course. There's some background noise. Hello, Camilo, I think you have some background noise there. If you could turn off your mic.
Sorry.
Yeah, thank you. So as I was saying, excuse me, an understanding of the elements of differential geometry and associated tensor analysis will afford us interesting and kind of deep interpretations of aspects of plastic deformation, such as dislocation, densities, and incompatibility conditions associated with elastic strain, and will lead us to an understanding of why it is that plasticity generally prevents a body from being entirely stress-free, even if it's unloaded, even if there are no loads applied to the body. I recommend, if you can see this book I'm holding up here, a nice small book by Fluga called Tensor Analysis and Continuum Mechanics, published by Springer in 1972. So it's rather old, but this aspect of the subject is quite classical. And the notation used there is compatible with what we're doing here. And it's a nice background reference to have that makes contact throughout with ideas in continuum mechanics. So, by the way, as you probably know, one of the main applications of differential geometry is the kinematics of a continuum that we're familiar with. We'll connect this subject to kinematics shortly. Some historical context. The subject basically started with, developed initially with the work of Gauss. You've heard of Gauss's work in connection with differential geometry of surfaces. Later extended by Riemann, introduced the notion basically of Riemannian space. So you can think of a two-dimensional curved space like a surface as a Riemannian space. In 4 dimensions, in space-time, Riemannian space is associated with gravity. Einstein's general relativity is associated with a Riemannian space. So my objective is, after introducing this subject, you'll be able to read all kinds of beautiful physics without any trouble whatsoever, including relativity and other developments. And we'll see here in the course, as I mentioned, that differential geometry has a major role to play also in the understanding of plastic deformation. So let's begin with a discussion of some aspects of this subject's quite classical. For the moment, let's confine attention to Euclidean space, or the space of our ordinary experience. Essentially, you can think of a Euclidean space as being a manifold space that can be covered entirely by a single Cartesian coordinate system, x1, x2, x3, or xyz if you prefer. Each point in the space then can be associated with a unique set of Cartesian coordinates. And so we can establish a so-called position vector, or point P in space, let's say. In terms of Cartesian coordinates, let's introduce an orthonormal basis, the standard orthonormal basis associated with Cartesian coordinates. And we can introduce a position vector then, which is the difference of the positions of point P and the position of the origin. that position difference then is a vector. It can be decomposed in our standard orthonormal basis as usual. I'll use this placement of indices, index upstairs and index downstairs. Whenever you see a diagonally repeated index like this, one up and one down, you sum over the range of that index, in this case from 1 to 3. So we'll invoke that convention throughout for reasons that will become clear. Okay, well, in Euclidean space, we can always use Cartesian coordinates to cover the whole space. Sometimes it's advantageous to use curvilinear coordinates, for example, when you're describing the geometry of a surface embedded in three-dimensional Euclidean space. Then coordinates intrinsic to the surface itself will necessarily be curvilinear. They won't be rectilinear like Cartesian coordinates. So quite often it's advantageous to introduce a set of curvilinear coordinates. So I'll call them theta super 1, 2, and 3. And to write then the Cartesian coordinates as functions of the curvilinear coordinates. So a standard example would be, say, a polar coordinate system in which you write the Cartesian coordinates in terms of radius, r, azimuthal angle, theta, axial coordinate, z. Those r, theta, and z coordinates, those would be curvilinear coordinates. We can write the Cartesians in terms of those, so that we can then construct a position vector in terms of the curvilinear coordinates. We can do the same, for example, in spherical coordinates, or any coordinate system you can conceive of. We'll suppose that, at least locally, the point in space is in one-to-one correspondence with the curvilinear coordinates. That's the case globally if you use Cartesian coordinates. But in general, with curvilinear coordinates, you cannot guarantee a global one-to-one correspondence between the point and the coordinates. For example, in polar coordinates, this one-to-one relationship breaks down at radius equals 0, for example, or at the pole of a sphere in a spherical coordinate system. So we'll assume, however, that those are isolated points where this one-to-one relationship breaks down, so that almost everywhere in the space we have a one-to-one correspondence between the point in space and curvilinear coordinates, theta 1, theta 2, theta 3. Okay, well, with position vector given as a function of the curvilinear coordinates, we can invoke the chain rule to write the differential dx in terms of the differentials of the curvilinear coordinates, sum on I from 1 to 3. Here we've induced 3 vectors, dx, d theta I. For each I, that's a vector, we'll call it g sub I. Okay? And we'll use the common notation to denote a partial derivative with respect to the ith curvilinear coordinate, just to save space. Okay, so the GI then are these derivatives. If we write the position vector in terms of Cartesian coordinates and write those in terms of the curvilinear coordinates, as we've done here, then we have an operational way to compute these vectors G1, G2, G3. Just form the matrix of partial derivatives of the Cartesians with respect to the curvilinears, multiplied by the orthonormal basis associated with the Cartesians, sum on J, and you have these 3 vectors, G1, G2, G3. And these will vary from point to point. They vary with the coordinates in general, because these will be some functions of the coordinates. And so they change from one point, P, to another. These G's are called the natural basis vectors induced by the curvilinear coordinates. And yes. Please, go ahead. Is there a question?
The superscript of in the yes. I mean for GI equals
so so G sub I here, there's a theta super I, but it's below the line, right? So you can think of it, it's in the basement So even though it's a superscript, because it's below the line, we regard it as a subscript to match with a subscript. Okay, does that help to remember the notation? So
yes, I'm asking is X J E J?
yeah.
Yeah. Okay.
What about it? There's a superscript J, a subscript J here. Use sum on J.
Yeah, I see.
Yeah, yeah. Is that clear? Okay. Okay, so
Yes.
these G subscript with subscripts have a simple geometric interpretation. Suppose I hold theta 2 and theta 3 fixed and consider a curve generated by varying theta 1. Okay, so we have x of theta 1, theta 2, theta 3, as we've just indicated. And just imagine incrementing theta 1 by the amount theta while holding theta 2 and theta 3 fixed. When I do that, I generate a curve. Okay. And G sub 1, let's say, is the derivative with respect to theta 1 at this point P. As usual, the derivative is just the limit of a difference quotient. The limit of 1 over theta, this difference here, between theta 1 and theta 1 is just theta. The limit as that goes to 0 of 1 over theta times the change in x, which is the chord between this point and this one. In the limit, as this point moves to P, the chord becomes tangential in the limit. So G1 is ultimately tangential to the theta 1 coordinate curve on which the other coordinates are fixed. And it's directed along the direction of increasing theta 1. So this gives you a way to visualize these G's with the subscripts. And so likewise, G2 is tangential to the theta 2 coordinate curve, the curve on which theta 1 and theta 3 are fixed, and so on. Okay. We would like to be able to use these G's that we've constructed, 3 vectors, as a basis, and so we need to examine conditions under which that's possible. It happens that the GI are linearly independent in 3-dimensional space, if and only if this determinant of partial derivatives of the coordinates with respect to the Cartesians with respect to the curvilinear coordinates is not 0. So I made a mistake here in the notes. I wrote equals 0. It should be not equal to 0. Okay, so make sure you correct that. And that's true if and only if it turns out the scalar triple product, or the box product of the 3 G's, is non-zero. So let's establish that. Let's establish the, let's write down an expression for the scalar triple product or box product. G1 is dxk d theta 1 ek and so on for G2 and G3. And I'm using different indices, for summation indices in each case to be careful to avoid conflict. When I collect terms, I have a scalar triple product of ek, ei, and ej. That's just the conventional permutation symbol e sub ijk. So in this case, I get e sub kij times these partial derivatives. If you expand this out, triple sum on ki and j, you will find that you simply have the formula for the determinants of the 3x3 matrix of partial derivatives of xi with respect to theta j. So for the G's to constitute a basis, we know that that means they have to be linearly independent, which means the scalar triple product should be non-zero, if you recall. Similar discussions in, say, 185 or continuum mechanics. A set of vectors is linearly independent in 3 dimensions, if and only if their scalar triple product is non-zero, which means this determinant should be non-zero. That determinant being non-zero means that the relationship between giving the Cartesians in terms of the curvilinear coordinates, say through functions x hat, I, are locally invertible. That is, local invertibility of these relationships is equivalent to this determinant being non-zero. That's by the so-called inverse function theorem, which we invoke very often in mechanics. So these will be locally invertible then if and only if the set of G's at a material point, or not a material point, but a point in space, the set of G's at a point in space constitutes a basis. Okay, so our local invertibility assumption ensures that the G's are linearly independent. Local invertibility means, of course, that we can write the curvilinear coordinates as functions of the Cartesians in the vicinity of a point in space. The Cartesians are the projections of the position onto the jth element of the orthonormal basis. These are fixed, these EJ. The variable is in this function is the x. So this defines a function of position x. Okay. So for convenience, for no other reason than convenience, we can choose the coordinates such that the scalar triple product that we've discussed is positive in this order, G1 dot G2 cross G3, so that the coordinates then form a right-handed coordinate system, entirely analogous to a conventional right-handed Cartesian coordinate system. Having found that the thetas can be written at least locally as a function of position, we can take the gradient of these functions with respect to position x. So let's take the gradient of theta super I with respect to x. When we do that, we get three vectors. We'll call them G super I, in contrast to the G sub i's that we had previously. So for example, G super 1 is perpendicular then to the surface on which theta 1 equals a constant. So if you set theta 1 constant and allowed theta 2 and theta 3 to vary, then you have a surface parameterized by the coordinates theta 2 and theta 3. And the gradient of theta 1, evaluated on that surface, is perpendicular to that surface, right? From properties of gradient that you know about. So these superscripted G's are orthogonal to the surfaces on which the corresponding coordinates are fixed, one at a time. Well, we can use the chain rule to write these in terms of Cartesians if we wish, because in principle we have the curvilinear coordinates as functions of Cartesians. This is just the Cartesian formula for a gradient. Put in theta 1, let's say, d theta 1 dxj ej is the Cartesian formula for the gradient. A moment ago, we established that the subscripted G's, the so-called natural basis vectors, do indeed constitute a basis because of the local invertibility assumption that we've invoked. It turns out that the superscripted G's, under the same conditions, also constitute a basis. The way we can establish that is by showing that their scalar triple product is non-zero whenever the scalar triple product of the subscripted G's is non-zero. So let's compute that scalar triple product using the formula here for the superscripted G's, one at a time. Okay, theta 1, theta 2, theta 3, again, different summation indices, in this case k, I, and j, so that we avoid inconsistent use of the summation convention. We again have the standard permutation symbol, ek dot ei cross ej gives you e sub kij, the usual permutation symbol you know about, equal to 1, minus 1, or 0, according as the subscripts are an even permutation of the numbers 1, 2, 3, or an odd permutation that will give you minus 1, or if any two subscripts are equal, then you get 0. If you expand this out, do the triple sum on ij and k, you will find that you have evaluated the determinant of this matrix, matrix of partials of the thetas, the curvilinear coordinates with respect to the Cartesians. And that's just the inverse of this matrix, right? The reason being that if you write, one way to write the a chain rule representation for d theta I, d theta k, let's say, would be d theta I dxj, dxj d theta k. But d theta I, d theta k is just the Kronecker delta, ones or zeros, depending on whether the indices are the same or not. So these matrices are inverses of each other. This is just the unit matrix. So this determinant will be the reciprocal of that determinant. We established previously that this determinant is non-zero, so this reciprocal makes sense. Therefore, this determinant will be non-zero, and so with the scalar triple product will be non-zero. And in fact, it has the same sign. The bars here are not absolute values. It means determinant. That determinant is the same size as this, same sign as this one. So this scalar triple product is again positive under our assumptions. So it's also a right-handed basis. Certainly not orthonormal. Okay. A useful property relationship between the superscripted and subscripted G's is this. The superscripted G's, remember, were the gradients of the theta super i's. Using Cartesians, we have this. The subscripted G's were the partial derivatives of the position vector with respect to the thetas. So we have this. This dot product gives us a Kronecker delta, KL, sum on L to get an XK here. Sum on K, and you just get this. This is just a chain rule representation of this, which is the Kronecker delta. So G super I dot G sub J is the Kronecker delta. For this reason, you can think of the vectors as being somehow reciprocal to each other, right? So the superscripted G's are often called the reciprocal basis or the dual basis associated with the subscripted G's. So these subscripted G's are called the natural basis or tangent basis. Superscripted G's, the dual basis associated with them. Here's a nice figure which has been reproduced from this book, Green and Zerna, a nice book called Theoretical Elasticity. Somewhat old, but the concepts are still current. So imagine, here's our point P in space. We draw three coordinate curves emanating from that point. The theta 1 curve on which theta 2 and theta 3 are constant, theta 2 curve on which theta 1 and theta 3 are constant, theta 3 curve on which theta 1 and theta 2 are constant. So we have the three coordinate curves. We also have three coordinate surfaces. For example, suppose theta 3 has a constant value at this point. Right? We can sweep out a surface, parameterized then by theta 1 and theta 2. And here's the surface theta 3 equal constant. Here's the surface theta 1 equal constant here. Here's the surface theta 2 equal constant. We establish that the subscripted G's are tangential to the coordinate curves and point in the direction of the increasing coordinates. So here's G sub 3 is supposed to be tangential to this curve. G super 3, on the other hand, is orthogonal to this surface at that same point. So they're not aligned with each other, but G sub 3 dot G super 3, according to the previous page, would be delta 3, 3, which is 1. Okay, so you have an idea then of geometrically of what we're talking about. So for example, on this surface, theta 1 equals constant, say the constant C1, you put in the constant C1, and you have then a vector valued function of theta 2 and theta 3. That would just simply be the parametric equation of this surface here, and so on. Okay, well, it'll be convenient and useful to extend the notion of permutation symbol. Let's have a look at our conventional permutation symbol equal to 1, -1, or 0, and make this combination sum on I, j, and k, and r, s, and t are fixed. The result we'll call epsilon sub r, s, and t. Sub because r, s, and t, although superscripted here, occur below the line, so we can regard them as subscripts. If you're ambitious, you can expand this out for any values of r, s, and t fixed in the range 1, 2, or 3. Each time when you expand out the triple sum on I, j, and k, you will obtain the determinant we had before times the value of e sub rst, were corresponding to the r, s, and t values that you fixed before doing the triple sum here. Okay, so we can also define an epsilon with superscripts. The theta's on top now. The Cartesians below, again, sum on I, j, and k. What you will get for the fixed values of r, s, and t that you select is the original permutation symbol times this determinant. Actually, why don't you amend the notes yourselves to put the r, s, and t upstairs here, make them superscripts, where e super rst is defined to be exactly the same as e sub rst. And that way it will be more consistent with having the r, s, and t superscripts over here. So I suggest you make that change. I should have done so here. So that e super rst is just exactly equal to e sub rst. Okay. This determinant, on the other hand, is the reciprocal of this determinant. We get this. Well, this allows us to extend the conventional interpretation of the permutation symbol. Let's take the cross product of gi with gj using the expression for gi, which is dxk d theta I ek, and the same for gj. This is our conventional permutation, eklm em, in terms of the orthonormal basis. So we have this. On the other hand, em we can write as delta sub mi, Kronecker delta times ei. Delta mi is partial xm with respect to xi. Okay. Turns out in Cartesians, whether you write superscripts or subscripts is immaterial, so that's why I've been a bit sloppy here and written delta sub mi. We can write the Kronecker delta this way, and then we recognize that as simply the formula for the gradient of xm, the Cartesian, the mth Cartesian coordinate. Using the chain rule, I can write that gradient this way in terms of the gradient of the curvilinear coordinates, sum on r. So that's dxm d theta r. Now this is g super r. So put that here and use the definition of the subscripted epsilon that we just had, and you will find that gi cross gj is epsilon sub ijk, g super k. So again, a diagonal sum on k. And that extends the conventional definition, right? For example, E sub I cross E sub j is E sub ijk ek. That's the Cartesian cross product formula. In the same way, we can write the cross product of the superscripted g's, the dual basis elements, using the definition of the superscripted epsilon. We will get simply this formula with a diagonal sum on k. Okay, so that'll be handy later on when we make extensive use of these natural basis and dual basis. Having these subscripted G's, we can take their dot products, and that generates some components, some scalars or matrix elements, G sub ij. And because the dot product commutes, that's the same as G sub ji. So we can make a matrix of elements, G sub ij, which is symmetric. Those are called the components of the so-called metric tensor. We'll talk about in more detail. In the same way, we could take dot products of the dual basis elements that would generate elements of a matrix we'll call G super ij. Again, the dot product commutes, so this will be a symmetric matrix. G super ij is the same as G super ji. And that we'll call the dual metric tensor, or the components of the dual metric tensor. So this is just a definition so far based on these dot products. Well, we can immediately put these matrices to use. For example, because the superscripted G's constitute a basis, we can write any vector we want as a linear combination of those basis elements. For example, let's do that for the subscripted G's. So take any of the subscripted G's, fixed I, expand it as a linear combination of the basis elements or dual basis elements, G super j. So I have a sum on j and I is fixed. Okay, so that's simply allowable by virtue of the fact that any subscripted G is a vector and the superscripted G's constitute a basis. So it can always write that vector as a linear combination of the superscripted G's for some coefficients a sub ij. Well, we can immediately compute those coefficients. We could take a dot product of this result with G sub k. Of course, that defines our matrix G sub ik. Put in G sub I as a sub ij G super j dot with G sub k, and use this reciprocity relationship G super j dot G sub k is Kronecker delta super j sub k. Sum on j, this becomes an a sub ik. So these coefficients are none other than the G sub ij's that we introduced. Okay? In exactly the same way, or analogous way, you can show that the superscripted G's are this linear combination of the subscripted G's, where the coefficients are the elements of the so-called dual metric. Okay, so we can use this matrix G sub ij to effectively lower the index on the superscripted G's to give the subscripted G's by carrying out the sum on j. Vice versa, we can use the dual metric components to effectively raise the index on the subscripted G's to give the superscripted G's by carrying out the sum on j for each fixed I. Okay, well, let's have a look at this exercise here. We can write the superscripted G's, of course, in this way. Kronecker delta I sub k, G super k, sum on k, and you just get G super I. We can write G super I in this way, as we've just seen, we just claimed. You can show yourselves. And we can write the subscripted G's this way. So put them all together. Be careful not to overuse the summation index, right? Use the j only once, the k only once as a summation index. And the I is fixed. So comparing both sides of this outer equality, you get this parenthesis multiplying G super k equals 0 for each fixed value of I. And of course, there's an interior sum on j going on here. So this is 3 vector equations. Because G super k is a basis, the only way you can have 0 is if each coefficient for each fixed subscript k is separately equal to 0, which means you have this result. And that simply means the superscripted G's are that matrix is the inverse matrix of the subscripted G's. Okay, provided that an inverse exists, right? So we need to show immediately that G sub ij is indeed invertible. If it is, then the superscripted G's are just the inverse matrix. So let's let scalar G just be, or the number G be the determinant of the subscripted G matrix. Again, the vertical strokes mean determinant. Then from this formula here, the determinant of the superscripted G's would just be the reciprocal of that, provided that that determinant G is non-zero. Well, the subscripted G's, those are gi.gj, g sub I dot g sub j, which we can write this way in terms of Cartesians. And that, because this is the Kronecker delta, this is simply the sum on k of this product. Here I'll make an explicit summation sign because I don't have it, the k's repeated diagonally, right? So I'll make the summation sign explicit. This is just the product of two matrices. So the determinant of this is the product of the determinants. We established previously this local invertibility assumption between the Cartesians and the curvilinears, meaning that this determinant is not zero, so its square is strictly positive. So G, this determinant, is strictly positive. And so that establishes the invertibility of the matrix Gij. So this is okay here. The G super IJs are indeed just the inverse matrix. We can say more. Imagine dx non-zero. Dx, if you recall, is just dx partial x with respect to theta I, d theta I. So that would be g sub I, d theta I sum on I. If dx is non-zero, then its inner product with itself would be the squared norm of dx would be strictly positive. That would be equal to this in terms of the natural basis elements. This is our matrix G sub ij. If dx is not zero, that means d theta I is non-zero for at least one I, right? That means at least one of the d theta super i's is not zero. We have this essentially, this is then a positive definite quadratic form in these d theta i's, which means the matrix Gij is positive definite. Of course, that would imply that the determinant is positive as well. And therefore, the inverse is also positive definite. You can easily establish that. Previously, we wrote these permutation components with the epsilons as the determinant of, sorry, this determinant here, right, without the square. We took that determinant to be positive previously. Well, rather, the determinant is simply then the positive square root of G, which we can write here. So we can simplify our notation a little bit. This is somewhat easier to remember, these permutation-like quantities we had before. We can show that these are, in fact, the components of a third-order tensor, provided we insert the square root of G in front. Likewise, these are the components of a third-order tensor. Okay. And here I'm making explicit the fact that the ordinary permutation symbol, I'll define it with superscripts or subscripts to be the same, just to be consistent with this placement of indices here. Okay. So using curvilinear coordinates, gives us a certain flexibility with respect to choice of bases. We have two sets of bases to choose from instead of the single set associated with Cartesian coordinates, for example. So we have two ways to represent a given vector v in our three-dimensional space, either using the g's as a linear combination of the subscripted g's, or as a linear combination of the superscripted g's. So far, all these coefficients, v super I and v sub I, are just the coefficients in the two linear combinations. And we would call these the certain components of the vector v in the natural basis, and these would be other different components of the same vector in this different basis, the dual basis. We can quickly relate these components to each other. Well, let's first have a look at what they are geometrically. If we take, for example, this representation, the first one, and dot it through with G super J. So we have V dot G super J. Use this representation of V in terms of the natural basis. Use the reciprocity relationship, G sub I dot G super J is the Kronecker delta super J sub I. Sum on I, we're just going to be left with B super J. Likewise, if we instead use this decomposition of the vector V and dot it through with V sub J, we get B sub I, G super I dot G sub J, Kronecker delta again, sum on I, you get V sub J. So V super J, you can interpret as the projection of V onto the dual basis elements, G sub super 1, G super 2, G super 3. V sub J are the projections of the vector into the natural basis elements. I'll come back to this terminology a little bit later. In the classical literature on this subject, the subscripted components are called covariant components, for reasons we'll see later. The superscripted components are called contravariant components. That's because of the manner in which they transform under coordinate transformations, but we're getting ahead of ourselves. We'll see that later. So far, we've established that we can write a vector v in these two ways, using the projection of v into the natural basis elements multiplied by the dual basis, sum on I, or alternatively, as the projection of the same vector v into the dual basis elements multiplied by the natural basis elements, again, sum on I. Let's have a look at these two representations of the vector v in terms of the subscripted components or the superscripted components, or alternatively in terms of the dual basis or the natural basis. From what we've done before, we can interpret G sub I as G sub ij super G super j, if you recall what we've just done a few moments ago. And then collect the outer equality in this form as some terms multiplying G super j equals 0. And of course, there's an interior sum on I taking place in here for each fixed j. Because this set is a basis, this can be 0 only when, for each j, we separately have the parenthesis equal to 0, which means the subscripted v, the components, are related in this manner to the superscripted components. So we can use this so-called metric tensor. Let's go back a moment. The reason G sub ij is called the metric tensor components is because it essentially gives us the squared length locally of a vector. Metric means meter or length, and so Gij furnishes us with a way to locally measure length in space. Okay, and in the same way, you can establish that this relationship between the superscripted and subscripted components of the vector. So for obvious reasons, this operation here is called lowering the index. You can use the metric components to lower the index on the vector, on the superscripted components to get the subscripted components. And you can use the dual metric or the reciprocal metric components to raise the index on the subscripted components of the vector to get the superscripted components. And so these are in one-to-one relationship with each other because the matrix is invertible. Okay. We can do other familiar things like take a dot product of arbitrary vectors, say two vectors u and v. We can, for example, write them both in terms of the natural basis elements. These would be the components of u and the components of v. Take the dot product, these numbers. It's a linear operation, so the numbers can be collected in front. Then we have g sub I dot g sub j. Gives us our matrix of metric components. So that's one way to write the dot product using the superscripted vector components. So there's a double sum here taking place. 9 terms altogether. Another way to write that equivalent way is by noticing, let's do the sum on j first. So put a parenthesis around v super j and g sub ij. If you sum on j, you simply get v sub I, and then perform the sum on I. Okay, so that's another way to write the dot product in terms of using the components. Yet another way is to regard u super I as the indexed raised version of u sub j using the dual metric sum on j. So here's a third way of writing the dot product using the dual metric. And finally, the fourth and last way would be to regard v sub I as just the index lowered version of v super j, right? v sub I g super ij is v super j. So we have this fourth way of writing the dot product. And you'll see all ways used frequently. Okay.
Professor, can I ask you a question?
Sure.
In this expression of the dot product, we have multiplication of components on different bases. I don't know, for some reason for me it doesn't seem correct, but based on the algebra it seems correct.
Well, it's the same. These are just, they're the same basis elements. It's just that we do them one at a time, right? G sub 1 dot G sub 2, G sub 1 dot G sub 3, and G sub 1 dot G sub 1, and so on, right?
I'm talking about the final result, U superscript, V subscript.
No, this is U sub J.
Okay.
Oh, okay. Let's see, I think, okay. I'm sorry, I confused you. That's wrong. What I said, so keep the V sub I as it is, and regard U sub I as the index raised version of Uj, right?
Okay.
U super I is U sub j, G super ij, right? In other words, this is just a finite sum.
Yeah.
So we can multiply the terms in any order we like, right?
Yeah. Okay.
So now I keep the U sub j, and I regard I can use the fact that V sub I G super ij is just V super j.
Yeah.
Okay. So so here I've written U super I is U sub j G super ij. You might have preferred to see the G right in here, but because it's a finite sum, I can multiply the factors each term in the sum, you know, I can commute the products, right?
Yeah.
Yeah.
Okay.
Is that better?
I think, shouldn't we have both subscripts?
This is two subscripts on the components, yeah, and the G superscripts. Here we have components of the vectors.
I see. You have them in the same basis, and then you just use the different symbol. Okay, I see. Yeah. Okay, thank you.
So I could have started with the subscripted components. In other words, I could have written U sub I G super I dot U sub V sub J G super J, and then this would immediately have given me this line right here, right?
Yeah.
So it's an equivalent thing.
Okay. Yeah. Okay. Thank you.
Yeah, it takes some practice. In fact, this little book by Fluga, if you want something to hold on to get accustomed to the notation, I would strongly recommend it. It's a very good book to learn from.
Okay.
Yeah, and I think it's quite an expensive paperback. Okay, let's go on to tensors, say second order tensors. Examples being strain or stress and so on. What we can show is that the tensor products, for example, of the natural basis vectors form all their tensor products. So there are 9 of these altogether, right? For I and j separately ranging over 1, 2, and 3, you form all these tensor products. There are 9 of them altogether. Interestingly, we can show that this set of tensor products is a basis for the linear space of second order tensors. The way we show that is quite simple. Let's form a linear combination of these elements. Double sum on I and j. So there are 9 terms here. So this is a general linear combination of all the elements of this set. Linear independence, so to be a basis, with of course this set has to be linearly independent. So we want to establish that the only way for this linear combination to be 0, the 0 tensor, is if all the coefficients are separately equal to 0. That's just the definition of linear independence extended to a linear space, essentially a 9-dimensional linear space of second order tensors. Well, so I'm going to force this linear combination to be 0. And then I'll see, I want to conclude that the only way that can be true is if all these coefficients are separately 0. Well, if this is 0, then I can operate on any basis element, let's say G super k, and the result is the 0 vector. Right? The 0 tensor operating on any basis element is the 0, any vector at all, is the 0 vector. Excuse me. Okay, I hope you don't hear my dog in the background, he's barking. This operation here gives me a dot product, G sub j dot G super k with G sub I left over. And I carry the alpha super ij. This is now the Kronecker delta from this reciprocity relationship we established. Sum on j, so to get Kronecker delta super k sub j, sum on j gives me alpha super ik with gi left over. So these are 3 vector equations. For k fixed equal 1 or 2 or 3, I get a sum on I for each k. So each of these 3 vectors indexed by k is equal to 0. But since the g's, these natural basis elements are indeed a basis, the only way that can happen is if for the fixed k that I chose in this set, all the coefficients, alpha super I for that value of k, have to separately be 0, right? So we've established that all of the alpha ik's are 0. In other words, this set is a linearly independent set. And the crux of the matter is that we assume that this linear combination was the second order 0 tensor, okay, which has a matrix just equal to 0, all zeros. So that means we can write any second order tensor we like as a linear combination of these basis elements that we've just introduced. just as we did for vectors, right? We wrote vectors as linear combinations of the basis elements. So here, in this case, I have a basis consisting of the tensor products of the subscripted G's. These superscripted components here, coefficients of the linear combination, are called the contravariant components of A. Just a word. Don't be concerned about it. Well, let's see. I'd like an interpretation of the coefficients just as we had a while ago for the vector components. To that end, let's operate on, say, the jth element of the dual basis, both sides of the equation. We get this. This tensor product operating on G super J gives me a dot product, the GK times the dot product, GL G super J, which is a Kronecker delta. Sum on L, I get AKJ with the GK remaining. Well, I want to get these components by themselves, so the obvious thing to do is dot multiply everything by, say, a superscripted G, an element of the dual basis. Then that would convert this to a Kronecker delta, right? So for example, G super I then dot A G super J would give me this product, Kronecker delta, sum on K, and I get A super IJ. So I have an interpretation of this matrix, A super IJ, as essentially the projection of the tensor A into this set, G super I and G super J. Another way to write that using, remember, we talked about the dot product of two tensors using the trace definition of dot product of two tensors, say capital A and capital B. You can work out using that trace definition that these are simply the dot product of the tensor A with this tensor here. And so this is in fact another basis for tensors, G super I tensor product G super J. Well, we can write the same tensor A, which we've written in terms of superscripted components using this basis here on top. We can write it alternatively. We can show alternatively that these tensor products of the superscripted G's also constitute a basis, essentially the same method that we used on the previous page to establish linear independence. We can use the same argument to establish that this is also a basis. Also, this is a basis with one element subscripted and the other element superscripted, say left subscript, right superscript. And also, this is a basis, left superscript, right subscript. So we can decompose the tensor in terms of those alternative basis elements. In doing so, we introduce subscripted components. Then we introduce mixed components, say I up, J down. I comes first, so I'll put a dot under it, so so in other words, the first slot has already been used by I, and then the second slot goes with J to go with this combination. And I can have another set of so-called mixed components. I downstairs takes the first slot. The second slot is taken by J upstairs. Okay? And these components also have names. The subscripted components are called covariant. These components are called the left mixed components, if you like, for lack of a better terminology. These components are called the right mixed components. And a similar calculation to what we've just done shows that the subscripted components are simply the projections of the tensor into these basis elements consisting of the natural basis. These are the projections of the tensor into these basis elements, G super I tensor product G sub J, and so on. So one encounters various different ways of writing a second order tensor. We can relate those components to each other just as we've done in the case of vectors. So for example, let's take this representation of a tensor with subscripted components and operate with, say, operate on an element of the dual basis G super M, okay? So we have this representation of A G super M. Alternatively, we can take the original representation, operate, I've been hasty in my writing here. I have a G super M, it should also be here, G super M. Okay, that's important to note. So make a note, please. This is G super M, not sub M. You can imagine it's easy to make notational mistakes in the subject. G super M gives me a Kronecker delta super M sub J. Sum on J, I get AI super M, G sub I left over. Over here, the dot product gives me the dual metric components, G super LM. So I have that times the A sub KL, G super K. Okay? Now I want to get rid of the basis elements to isolate the A super IM. The obvious way to do that is to dot multiply the equation through with G super N. That converts this to a Kronecker delta super N sub I. Sum on I, you get A super N M on this side of the equation. Over here, I get a G super K dot G super N gives me the dual metric component G super Kn. So I have this expression, this formula, that generates the superscripted components in terms of the subscripted components. Remember, when we were talking about vectors, we needed one matrix of dual elements to raise one index. Here, if we want to raise two indices, we need the dual metric matrix twice. And you can go through the same routine to show, for example, that if you start with the mixed components and you want to generate the superscripted components, you only need to raise one index. You do that this way using these components, or this way if you use these components. And in the same way, if you start with the superscripted components and you want the subscripted components, you need the metric twice to lower the indices, lower two indices. Okay, so this formula is essentially the inversion of this formula. Okay, so they're all those different variations on the same theme are established in exactly the same way. Okay. A very important object to us is the unit tensor, or the identity. We can write it in terms of subscripted components. Say I sub ij. Remember that the subscripted components, if we go back for a moment, let's see, where am I? The subscripted components of the tensor are obtained in this manner. So in place of A, we will put capital I, and that gives us this formula here. Of course, capital I on any vector is by definition the same vector back again. So this I G sub j would be G sub j, dot with G sub I, and you get the metric G sub ij, with these basis elements left over. If I like now, I can sum on I, and I know that the effect would be to convert this dual basis elements into the natural basis elements. So here's one way of writing the identity. Here's another way of writing the identity. I can also regard, let's see, G super j as the result of operating on G sub I with G super ij, as we saw before. So here's another way of writing the identity. I could write this by simply switching the names of the summation indices. I could write it as G super ji, G sub I, tensor product G sub j, and then use the symmetry of G super ji to write that as G super ij. And then I have yet another way of writing the identity. And I can interpret this, if I sum on I, G super ij, G sub I is just G super j. So here's yet another way of writing the identity. Okay? And by the way, let's say if I take this representation here, I can interpret that as Kronecker super I sub j, G sub I, that's the same as G sub j. So I have this. So this would be a left mixed representation of the identity. That would just be the conventional Kronecker delta. A diagonal matrix of ones, 1 on the diagonal and 0 elsewhere. Or I can write this as Kronecker delta super j sub I, G super I. And then I have a right mixed component representation of the identity with the same numerically equal Kronecker delta components. So the left mixed and right mixed components are the same in every coordinate system, just given by the Kronecker delta components. The other components depend on the dot products of the basis elements, and so they'll be different in different coordinate systems. But the mixed components are always equal to the Kronecker delta, which is kind of interesting. Okay, in the old days, and I mean in the 1800s, and late 1800s, early 1900s, people would define a tensor to be something that obeyed a certain transformation rule under coordinate transformations. Let's revisit that in this context. Suppose instead of using the curvilinear coordinates theta super I to locate a point P in space, suppose I use a different coordinate system, theta bar super I. For example, I might prefer to use spherical coordinates instead of polar coordinates. So an alternative curvilinear coordinate system I'll call theta bar super I. And suppose I can compute these theta bars in terms of the thetas, right? I can convert, in other words, I can convert, say, polars to spherical. That should be an easy operation. So I'll assume that is possible. And I'll assume I can do the reverse. I can convert spherical into polar. So that locally, at least, these relationships are invertible. Well, the original set of coordinates induces the natural basis elements by taking a partial of position with respect to the coordinates as before. Likewise, I can write the position vector in terms of the theta bars and take partial derivatives, and I get G bar sub I, the natural basis elements associated with the barred coordinate system. Doing so, I can also follow the previous procedure and generate the dual basis, the corresponding dual basis elements, G super I and G bar super I. Well, let's see if we can relate these to each other. G bar sub I is the derivative position with respect to theta bar I. I can use the chain rule to write that as dx d theta j d theta bar I, assuming I can locally invert these relationships. I can take the derivatives of that inversion. And then this, of course, is just the G super j without the bar, and I have this. So at my point P in space, I have this transformation formula for the elements of the natural basis. There's a sum on j here for each fixed I, 1, 2, or 3. So that involves a matrix operation, multiplying the elements of the natural basis to get the new natural basis elements. Likewise, the dual basis elements in the barred system are just the gradient with respect to the same position x of the barred coordinates. Use the chain rule again, and I get this relationship in terms of the original dual basis elements. And these matrices here, these coefficient matrices, are inverses of each other. So given one set of natural basis elements, I can compute the natural basis associated with any other coordinate system, as well as the dual basis. Okay, well, I can use either basis that associated with a point in space, use either basis to decompose my vector, say in terms of superscripted components, in terms of the natural basis in both cases for both coordinate systems. And the subscripted g's, by the same reasoning as I've used here, I can interchange the role of the barred and unbarred coordinates, and I would get this relationship. G sub I is this in terms of G bar sub J. Right? That's essentially the inverse of this relationship, or you could derive it directly. Now I have everything on the same G bar basis, so I'll take this outer equality. So this, I can collect V bar super J minus this combination, all multiplying G bar sub J equals the zero vector. Because the G bars constitute a basis, that means each coefficient has to separately be zero. Here I've simply changed the name of the summation index. In going from here to here, I've simply replace J by I consistently, and replace I by J consistently without changing the result. So here's how the components, the superscripted components, are related to each other. You can do the same thing for the subscripted components, and you get this relationship where these matrices here, these coefficient matrices, are inverses of each other. So here we have the origin of these strange terminology, covariant and contravariant. Notice that the subscripted components transform in the same way that the natural basis elements transform. The same coefficient matrix is involved in both here and here. So these components transform in the same way as the natural basis elements transform. For that reason, we call them covariant. They covary, they vary in the same way as the natural basis elements. Whereas the superscripted ones here vary in the opposite way in terms of the inverse. They invoke the inverse matrix, so we call them contravariant. It's just a kind of archaic terminology that has stayed persistent in the subject. These can be inverted because our local invertibility assumption concerning the two coordinate systems means that the matrix has an inverse. So we can invert these relationships, and we have the inverse relationships here. And you could do the same for tensors. I'll leave it to you to quickly derive the corresponding results for tensor components. For example, the subscripted components in the barred coordinate system, in terms of the dual basis in the barred system, have this relationship to the subscripted components in the unbarred system. So you can remember this easily. A sub ij bar goes with a theta bar I and a theta bar j. So wherever you see a bar here, you should have the barred coordinates in the same index position. That is downstairs, 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 below the bar here, below the floor, if you like. Okay, so it's although it looks complicated, it's actually rather easy to remember if you simply commit to memory some rules of thumb. Okay. A bar sub ij, you have a theta bar I downstairs, theta bar j downstairs, to go with the downstairs indices I and j here, and so on. So I'll leave it to you to derive the transformations for the other types of components. So in the old days, people would take this as the definition of a tensor. For example, a second order tensor, at least the downstairs, the subscripted components, the so-called covariant components, were defined such that this transformation formula holds. That was taken to be the definition of a tensor. And you see, we've simply induced that transformation formula from our modern definition of a tensor. And the reason tensors became so prominent in the first place is precisely because of this transformation formula. So for example, suppose you have a physical statement, some physical law represented by a tensor equation, say a sub ij equals 0, for example. If this is true in the theta I coordinate system, then the transformation formula guarantees that it's true in any other coordinate system as well, right? If these are 0, then these are automatically 0 because of the homogeneity of the transformation formula. That is, A occurs in a homogeneous way, degree 1. So if the A's are 0, the A bars are automatically 0. So any statement that's true in one coordinate system, you can always rearrange any statement you like as something equals 0, right? Any physical law that you express in the form a sub ij equals 0, if that statement is true in one coordinate system, it's automatically true in every coordinate system. And that means the physical law has the property of being invariant under changes of coordinate system, which after all, a coordinate system is something merely that we choose for the purpose of analysis, right? The physics involved should be insensitive to our sort of idiosyncratic choice of coordinate system. And so this transformation formula, exemplified here by this particular formula, and you can derive the other ones for yourselves, this transformation formula is the basic reason why theories about physics are based on tensor equations. Okay. We'll pick up the subject here. We'll talk about calculus using this formalism, gradients and divergence and curl and so on. But we're at the end of our period now, so I'll stop here and ask if you have any questions. It's something of a learning curve to get familiar and accustomed with the notation, but it's very widely used, and it serves you well to learn this subject as well as you can. Doing so enables you to read everything, and just about everything in physics, from the days of general relativity, let's say, or differential geometry of surfaces and so on. So it's well worth your while to learn the tools of this subject. Okay, I'll stop now and take some questions if you have any. And if not, then I'll see you next time. Okay, have a good weekend.
Thank you. You too.
Thank you. You too.